three different columns, or you could have three different rows. So it doesn't have to just be a two-way, but they also call this a frequency table. So you're comparing different categories basically when you're looking at these. And so just to see if you guys can kind of understand how to read the table a little bit, the data is really just in these four spots. And not all these tables will do this, so I apologize. A couple on the Math Excel assignment won't give you the totals, but underneath each column and at the end of each row, they have a total. Can you guys tell just from looking at the table, this is relating just whether a person is male or female and then right-handed or left-handed. So can you tell just how many people in the table are represented just from the information there? Like how many people are in this table total? Yes, this bottom corner here, the sum of the columns and the sum of the rows, they have to be the same, so there's 100 people here. Okay, how many people in this table would you say are female? Yes, ma'am. All right, how many are guys in this table? 52. All right, is it making sense? How many people are right-handed? And how many people are left-handed? Okay, perfect. All right, so if you can read the table, you can do these probabilities. Okay, now, find the probability, just a single thing, the probability somebody is right-handed. So out of all the group, there's only one requirement. How would I find the probability someone is right-handed looking at the table? I just randomly pick somebody. If I randomly pick somebody out of this group, what would you tell me the probability is I pick somebody that's right-handed? Yes, ma'am. 87 out of... Okay, now what is the probability I'd randomly pick somebody from this table and they'd be female? This would be 48 out of 100. And I probably should reduce that, right? So let me just do that real quick. I should be able to do that in my head. This would be 12 out of 25 if we reduce that lovely fraction. Okay, now we did and or statements in our last lesson. And I told you to think multiplication if you saw and, right? And addition if you saw or. And that's still true. But if you have the information displayed to you in a table, instead of trying to multiply probabilities, what I would tell you if you have a table like this, the probability that you pick somebody that is male and right-handed, you can actually just pick the information out from the table. It's one of the numbers in the table over 100. But don't try to think about this too hard. Tell me how many people in this table are male and right-handed. What do you think? Exactly. Just when you have an and statement, if you have a table, just find the intersection of the two things. So male and right-handed. So this would be 43 out of 100. Don't try to multiply. Just find that intersection on the table. An and statement is also called an intersection. So if you have a visual of this, this will be a little bit easier to calculate than trying to do separate multiplication if you have a table. Okay, so somebody tell me, what's the probability the person I pick at random would be female and left-handed? Yeah, exact. Find that intersection, female, left-handed, there's your 4. 4 out of 100, and then we can reduce that, that'd be 1 out of 25. Okay, now the or statement. This one is a little tricky, especially if you have a table, because unless you have a blank spot in the table, there will be an overlap if you have an or statement. So there's a couple ways you could do this, but it's not going to be when you have an or statement something you can just grab a number from the table and be done. And statements you can't. So male or left-handed. So just in general, the number of people that are male, 52, right? The number of people that are left-handed, sorry, this is right-handed, this is left-handed, can't see it on the screen very well the way I did that. The number of people that are left-handed is 13. And then I counted, in that case, the intersection twice. So when I counted up all the guys by just grabbing that total there, the 43 and the 9, And then when I counted the left-handed people, I went just down that column, I counted that 9 twice. So you just have to subtract that overlap off. So this 52 is their male, the left-handed is 13, and then the overlap, I counted that 9 twice. This whole thing would be over 100. I'm pretty sure this guy was 56. So let's see. 56 over 100, bless you, 56 over 100 definitely reduces to 14 over 25 if you got to reduce it. Okay, so kind of the same thing, and oh my gosh, I should have, let me pull this up just a little bit so you guys can maybe see the table at the same time. Okay, so female or right-handed. So you can't just grab this from the table in terms of just a number over 100 like you can do with an and statement to just find the intersection. So female, you got 48. Right-handed, you got 87. And then just grab it off that printer. Sorry. So when I counted the female and the right-handed, then you're counting these 44 people twice because they fall into both categories. So I'm going to subtract that off and then over 100 to get my probability. You guys are probably already done with this. So let's see. Should get 91 over 100, and that's not going to reduce. Is anybody having a question? Okay. Now, conditional probability, I'm just going to give you kind of like a little requirement here, but I'm not going to give you any problems that don't have this, so you won't have to worry about that. But a conditional probability, sorry, this is being weird. Probability event B will occur given that another event A has already occurred. So basically it'll say to you like, given you know this happened, what's the probability of this next thing happening? It can only exist when the two events are dependent. So the probability of the first one is going to affect the probability of the second one. And conditional probability of event B given that event A has occurred. I'm just going to show you the notation here. We would write it as P and then in parentheses B, and there's like a little bar. It literally just looks like a little vertical line and then A, and that stands for probability of B, which would be the second event given that A already happened. So you know that the A value happened. Okay, now I'm going to give you the technical formula for this, but then I'm really not going to encourage you to use it because it's way easier to do these problems in a little bit different way. But the technical formula for this is the probability of A and B divided by the probability of A. Okay, now, especially if you're working with a table, I would like never use that formula. Here's what I would do. I'm going to grab my little highlighter here. This little bar means whatever follows it is what's given to you. So I'm just going to jot that down. You don't have to write this. But whatever is the second thing, that is going to be given to you that has already happened, or you've already been in that category. So what's the probability I'm right-handed given that I know the person I picked out of this table is female? So this is the same table we were using above. I just moved it down a little bit. Okay, so if I am given that the person is female, I would literally only look at the row where I have the information about the person being female. So I know the person that I picked is female. So given that, what's the probability the person would be right-handed? And that first column is right-handed, that second column is left-handed, and I know I just covered those up. But given that the person is female, the number of females in the table, that would go on the bottom of the probability there. So whatever is given to you, the total in that either column or row, in this case it's a row, the total should be the bottom of the probability. So given that I picked a girl, probability they're right-handed, so that would be the 44 out of 48. And then I would just reduce that real quick with my lovely calculator. So this would be 11 over 12. So whatever's given, the total in that column or that row should go in the bottom of your probability. So this one says probability the person's female given that I know they're right-handed, which sounds really similar to the question we just did, but it's backwards, right? The last one I was given that the person was female, what's the probability they're right-handed? This one is saying I know the person's right-handed, what's the probability that they're a female? So given that they're right-handed, whatever that is, which is the total in that column there, that 87 right-handed people goes on the bottom. The number of females would then go on the top. So you can see this is a totally different probability. So it depends on what the condition is. So that one would be 44 out of 87, which does not reduce. But if you want to do a decimal, it's about 0.506. So any of these, if you want to do a decimal, you can do that. Or if you want to reduce the fraction, you can do that too. All right, so see if you guys can do these two at the bottom. So if I tell you what's the probability a person in this table is left-handed given that I know that they're male, how could I set up a fraction for that? Probability person is left-handed given that I know that it's a guy. What do we think? What would your, and you don't have to reduce it or anything, what would your fraction be? What do you think? Yes, ma'am. You know it's a guy, so it's going to be the 52, and left-handed, 9 out of 52, and I actually don't think that reduces, so I would just leave it alone. Okay, what if I told you what's the probability that I'm grabbing a male knowing that they're right-handed? Male knowing that they're right-handed. Yeah. Yes, ma'am. 43 over 87. And that one doesn't reduce either. Does anybody have a question? Okay, I'm going to give you guys a little bit different format for a way to calculate conditional probabilities here on the back. But before we do that, we'll do the tree diagram at the bottom here. So this is kind of a tricky problem, but it's actually not terrible. So they're just going to give you these probabilities to the side. So this isn't in a table, it's not in like a diagram or anything like that. It just gives you these percentages. We're going to calculate these probabilities. Okay, a randomly chosen person has a pet given that they have had a pet. All right, so these are kind of weird, but 39% have a pet now and have had a pet. 61 don't have a pet now. 86 have a pet, or have had a pet, sorry, and 14 do not have a pet now and have never had a pet. All right, so whatever is given, they don't write it as a probability here. So randomly chosen respondent has a pet, this would be like your bar here, given that the respondent has had a pet. So I'm looking for, well, I should have written the context correctly. It says 86% have had a pet. So this would go, the 86 would go on the bottom. I know it's given to you guys as a percentage, but you can literally just use the numbers. You could use a decimal, it would give you the same thing. But 86 have had a pet. And then it says 39% have a pet now. So randomly choose a person, they have a pet, that would go in that 39% category across the top. And I don't think that reduces, but I'm just going to check real quick. And it does not. So that's all you would have to do there. This one says randomly chosen respondent has never had a pet given. So this would be our bar. The respondent doesn't have a pet now. So you're looking for doesn't have a pet now, which is that 61. That should go on the bottom. Randomly chosen person has never had a pet. If you look through here, it says 14 don't have a pet now and have never had a pet. So the 14 would go on the top of the 61 to calculate the probability there. And that does not reduce. Does anybody have a question? Okay, the last thing we're going to talk about here is called a tree diagram. This is just kind of a way you can display different probabilities a little bit more visually. So I sort of stole this from the internet so you guys could get like one that was already done, but this just shows the action of just tossing a coin. Like, what would the options be? So they call this a tree diagram because they call those little arrows that look like a ray from geometry, they call those branches. And so basically the starting event is this, like the vertex of that right there. And then the outcome, if I flip a coin, heads or tails. And what you do is you put the probability, typically they put those as a decimal along the branch. So you're not going to see a lot of fractions. If you see a tree diagram, they'll use a decimal. So 50% heads, 50% tails. Now, this one's a little bit more elaborate, but building on that same one. So the way these work, if you want to calculate the probability of something, is you multiply along the branches. So this has heads and tails, and then it's flipping the coin a second time. So if I got heads the first time, I flip the coin again, my options again are heads and tails, the same probabilities. It's still 50% heads, 50% tails. The way this works, like if I wanted the probability I flip 2 heads, I just would multiply along the branches for that result. So heads twice would be 0.5 times 0.5. If I wanted this is maybe not the greatest example because all these probabilities are the same, but if I wanted probability like I flipped tails and then heads, it would be 0.5 times 0.5, and then I would just calculate the probability by multiplying those decimals along the branch for what you want. We're going to do one that has some different probabilities, so hopefully that'll make this make a little bit more sense when I show you the multiplication. Okay, so let's draw a little tree diagram here. It says school system compiled the following information from a survey sent to people who were juniors 10 years prior to this survey being given to them. So they've been out of, so they'd be like 27, let's say. Okay, 85% of the students graduated from high school. So that's kind of like where I'm going to start my little tree. So I'm just going to draw 2 branches. The outcome would be they graduated or they didn't graduate. Those are the 2 outcomes. And it says 85% of the students graduated. So I would just put like a little 0.85 as the probability that I would pick somebody that graduated. Does anybody know what I would put along the other branch? Like if 85% graduated, what would I put for didn't graduate? 0.15, exactly. The 2 branches, like wherever they branch off like this, the 2 together have to add up to 1. So that would be a total of 100%. So this would be 15. Okay, now it specifically says of the students who graduated from high school. So I'm going to come up, maybe I'll just do a different color here. Graduated from high school. 90% are happy with their present job. And so then the other branch from that would be they're not happy with their present job. So it says 90% are happy with their job. So I'm going to put 0.9. What would you put for the branch for not happy? 90% are happy. How many are not happy? 10. Okay, I was about to have a heart attack. All right, so 10. So just I'm going to put 0.1. All right, so then for didn't graduate, it says of the students who did not graduate high school, so the same branch here from the did not graduate, 60% are happy with their job. So I'm going to put 0.6. And how many then, what percent would not be happy with their job? 0.4. Okay, now we've got our tree diagram drawn, so we're going to use this to calculate a couple of probabilities here. Okay, so graduated and are happy with their job. What's the probability of that? So here is, I'm just going to do a little highlighter with these. Graduated and happy with their job. You would just go along the branch until you got to what you wanted the result to be. So graduated and they're happy with their job. So to calculate that, we would literally just multiply along the branch. So I would do the 0.85 times the 0.9. Now, these probabilities should never be more than 1. So keep that in mind when you're doing these. If you get a number that's bigger than 1, we may have messed up something in the tree diagram, but that would be 0.765, so like 76.5%. Okay, the second one says they didn't graduate, so I'd go here, and they're happy with their job. So that would go along those two branches right there. So I would do the green to match. So 0.15 times 0.6 there, which I think is 0.09. All right. Now, I want to actually, let me add one to the side here before I do letter C. I'm going to give you a conditional probability. So let's say I asked you, what's the probability the person is not happy given that they graduated? What's the probability the person is not happy if I give you that they graduated? It's just 0.1. Yes. Okay, so if whatever's given to you is one of the first branches, you literally just like don't even look at those probabilities. So graduated, given that they graduated, what's the probability they're not happy? It would just be the 0.1. You don't have to multiply or calculate anything there. Now, the last one I wanted to give you, this one is a little tricky because this just says, what's the probability they're happy with their job? And if you guys look here, right, there's two different ways that that can happen in that table because there's two different outcomes that end up with the person being happy. So we actually have calculated what we need to use for this part of the question before we did the question, but you have two different probabilities here. They graduated and they're happy, or they didn't graduate and they're happy. All right, so I'm actually going to take these two probabilities we just did right above here, the 0.765 and the 0.09. And how do you think I should combine those to get the total probability? These are the people that are happy with their job that graduated. These are the people that are happy with their job that didn't graduate. What would I do with these two numbers to calculate this probability that just in general the person is happy with their job? Anybody know? You can either add them or multiply them. Does anyone want to guess? What do you think? You add them. Yeah. All right. So I'm going to just show you. If you multiply them, that changes the probability down, right? So the number of people in this table that are happy with their job that graduated was 76.5%. You've got 9% more that are happy that didn't. So you actually want to add them together. Don't multiply them because that makes the probability lower. This would be 0.855 if we add these guys together. Okay, is anybody having a question?